So, hi everyone. My name is Yun Lu. Welcome to the talk, How Private Are Commonly Used Voting Rules. This is joint work with Ao Liu, Lirong and Vassilis Zikas. So, it probably needs no convincing to believe that voting data privacy is a big deal. In the news, we have seen examples of how politicians have exploited the huge amount of information that data mining companies have on every voter. But the question is, can we quantify privacy leakage? For example, how much privacy is leaked by this map of how people voted in the United States? In this work, we're curious about two things. One, can releasing election results break privacy? And two, does the voting rule we use matter? To answer these questions, we need a well-accepted notion of privacy. In 2006, Dork invented differential privacy, or DP, and it has since become the gold standard of privacy used by tech companies and even the US government. Can we answer our titular question with DP? Well, unfortunately, no. And the problem is that DP can only be used to study randomized voting rules. And this is the case for all previous works. They all considered randomized voting. But common voting rules are not random. I mean, can you imagine if the next president were decided on the flip of a coin? So even though differential privacy cannot be used to study common voting rules, it is still relevant for our work, so let's see how it works. Let X be a collection of votes for the color red or green. We have a function f which outputs f of x. To find the privacy of f, let's see an alternate reality where all the parties vote the same way except one person, Eve, who changed her vote from red to green. We say that f is dp if for all x and x prime differing by one vote, the output distribution of f on x and x prime differ by no more than epsilon and delta. And here, the smaller the epsilon and delta are, the more private f is. So to see why deterministic voting rules cannot be DP, let's look at the definition. Here, x, x prime, and y are all fixed. So this means that f has to be randomized, or else the probabilities are always going to be 0 or 1. And the solution is to take advantage of a data miner's uncertainty about the distribution of votes. What this allows us to do is treat x and x prime as random variables, which allows f to be deterministic. This takes us to the notion of distributional differential privacy, or DDP. Informally, it's the same as DP, but defined with respect to a set delta, which is a set of vote distributions. And the function f is DDP if, for all distributions in the set delta, the output of f differs by no more than epsilon and delta if we set one vote to different values a or b. What DDP allows us to do is to study deterministic voting rules as they are used in real life. As the first work towards this direction, we consider sets delta, which comprise of distributions with IID votes. And our contributions can be summed up with two main messages. One, deterministic voting rules already have pretty good privacy under DDP. And two, we show that different voting rules have an asymptotic difference in privacy via a dichotomy theorem. To show that most deterministic voting rules are already pretty private, we show an even stronger statement. That is, even if we output the exact histogram of votes, we get good privacy. What do we get? For epsilon greater than 0, we get that delta is exponentially small in the number of votes, which is considered negligible. For epsilon equal to 0, we get that delta is 1 over square root of n, which comes from the probability of a tie. Intuitively, a tie is a situation when one person changing their vote makes a lot of difference, and this is bad for privacy. To see that intuition in action, let's go back to the example of red versus green votes. Let f be the function that outputs the color with the most votes. So how private is f? Let epsilon equals to 0. We want to find delta such that the DDP definition holds. So what is the probability that red is the winning color given that Eve votes for red? Is the probability that the other two votes other than Eve have a tie between green and red, or when red gets both the other votes. On the other hand, if Eve votes for green, it's only possible for red to win if red is given by the other two voters. We see that these two cancel out, which leaves the probability of a tie between the two other voters. And this idea extends to arbitrary n, and is the core idea for our technique for our dichotomy theorem. Unfortunately, we don't have much time to go into GSR, but roughly, we show that for common voting rules like plurality, k-approval, and so on, the following hold. When the set delta contains the uniform distribution of votes, we get that epsilon is 0 and delta 1 over square root of n. If we recall from our first message, this is the privacy that's achievable by any voting rule. So this is in fact the worst case scenario in terms of privacy. On the other hand, when the set delta contains no unstable or tie-causing distribution, then we get a really good privacy of epsilon equals to 0 and delta exponentially small in the number of votes. In conclusion, we showed two main messages to answer our initial question about the privacy of common voting rules. What's next? One idea could be to study more complex distributions than ID votes. Or we could study the privacy of other kinds of voting data, such as age or location. Thanks for watching.